Hello and welcome to this PIR Live Event webinar brought to you in part by Partners in Research Canada. My name is Ben Hobbs and I will be your host today. If you're joining us live, remember that you can ask questions at any point by using the Q&A, which is located in the bottom center of your screen, and typing your questions into the pop-up window. I will relay these questions to our guest during the Q&A section of this webinar. If you see a question in there someone has asked that you would also like the answer to, feel free to prioritize that question by clicking the thumbs up icon just below their question. So without further ado, I would like to introduce our guest today, Dr. John Smol, Professor and the Canada Research Chair in Environmental Change in the Department of Biology at Queen's University. Thanks for joining us, Dr. Smol. I'll let you take it from here.
Thank you. Well, I'm very happy to be here. I enjoy doing these partners in research talks, and I've done several of them in the past. Just by way of introduction, I'm a professor at Queen's University, as Ben just told you, and I've worked on a large spectrum of issues that usually relate to water. I'm actually a lake biologist. I study lakes to see how they change over long time frames. Many people look at a lake from day to day, and I do that too. I study how a lake changes from May to June to July and August. But I also look how they change on hundreds and thousands of years. And I use lake sediments, the bottom of a lake, to do that. I'm not going to talk too much about that specifically here today, but we have ways that we can actually reconstruct how environments have changed, not just on years, but decades and on centuries as well. What I wanted to talk about today is I had a lab of about over 40 people, so it's a very big group. We work on all 7 continents. We have projects in South America and China and everything. But what I'd like to talk about today is much of the work that I've done has actually been in the Arctic, the Canadian Arctic. And I thought I'd reflect on the 35 years that I've actually been working in the Arctic. And I think you should see a screen now, hopefully.
That's perfect. We can see it.
Perfect. Excellent. So I gave my title Polar Journeys, Reflections on 35 Years of Environmental and Climate Research. So I'm going to take you up to where it's cold. It's cold now in Ontario, but it's even colder up there. It's also dark up there now because it's near the time when we have long periods of darkness. What I have, I start off with this open slide here, and that shows you even in August. That's a picture taken in August of one of the lakes I work on. It shows you that even in August, the warmest month of the year, let's say, you could still walk on the ice. Some of these lakes are permanently ice covered even in August. So I go fairly far north. Most of the pictures I'll show you are from what they call the high Arctic islands. And so if you look at, most people think of Canada and they stop thinking about Canada once the major land masses ended in the north. But then there's all these islands up there. That's also part of Canada, a very important part of Canada. And that's really where I do a lot of my work. So, but what I want to talk about is primarily climate change. And you can't just talk about climate change because we do many, many things with the environment, but primarily climate change. Here I have a picture of the Earth. And you've seen this from space probably many times. We call the planet Earth, but in reality, if aliens ever came to planet Earth, they probably wouldn't call it Earth. They call it water because more than 2/3 of the planet is water, is mainly oceans. And oceans actually are very important in how our environment works. Of course, we need water. We need fresh water. If you don't have fresh water, if you don't have water to drink, you'll be dead in a couple of days. So it's a very, by the same token, where there's water, there's life. So water is very important in how the environment works. That's one of the reasons I like working on water. It's very important. So there's the first thing that aliens would notice is that all the water on this planet, liquid water, and that's key as well. The next thing they'd notice is they'd look at the land and they'd be like a green skim on the land. And that was the second thing they'd think of. It's a living planet. And that's photosynthesis. Those are trees and other types of plants. And that's what drives our system forward. Trees are taking in carbon dioxide. They're releasing oxygen. And that the living planet and everything is actually based on that photosynthesis that those trees are doing. And the third thing they'd notice, if they look very carefully, they'd see a very thin layer around the Earth, which is our atmosphere. And our atmosphere is the air around us. but it's, you know, it seems enormous when you look up at the sky, but it's very thin. I use the analogy, if you have a globe on your desk, the thickness of our atmosphere is about the thickness of the varnish or the shellac that's on that globe. That's how thin our atmosphere is. But we, as humans, we've learned how to change the chemistry and the composition of that atmosphere, and that's what's causing a lot of the problems we have today. So I just thought I'd talk quickly about the greenhouse effect. And I think you probably know quite a bit about the greenhouse effect, but I would just give a big summary of how the planet works before I get into how we've actually changed that environment. So I think, of course, the Earth is down here at the bottom of that screen, and the sun, the ultimate source of energy is the sun, and the sun's rays, that's what heats up our planet. If it wasn't for the sun, we'd be frozen solid, obviously, and we wouldn't be here, obviously, we wouldn't even have a constellation. But the sun's rays heat the planet, and that works very well. And then some of the sun's rays are reflected. Not every piece of energy coming from the sun hits our planet. Some is reflected by clouds, by dust, and that goes away. But a lot of it does make it to the Earth. And then once it's on the Earth, then it's radiated back up into the sky. And if you go out on a hot August day and you put your hand on top of like a black, let's say, asphalt road, you'd actually feel sort of this heat coming off the asphalt or coming off the driveway. That's the outgoing energy. And for thousands and thousands of years, the sun's rays would come down, come from the sky, hit the Earth, heat up the Earth, and out would go an outgoing radiation. Now, some of that, not all the heat disappears. If all the heat disappeared, we'd be like Mars, we'd be a frozen planet. But always, because of greenhouse gases, and by greenhouse gases, that's mainly what I'm going to talk about is carbon dioxide, CO2, but also it's the same thing that plants take up for photosynthesis. Not just carbon dioxide, but there's other greenhouse gases like methane. And we've always had those on this planet, and that's what it absorbs some of that outgoing radiation. And it's always done that. And that's what we need. Otherwise, we'd still be frozen, because if all the heat coming in would be going out, we'd be a frozen ball, much like Mars. Some of it is heated. The problem is, because of what we do, because of burning coal, because of burning oil, what we call fossil fuels, we have been increasing the greenhouse gases in the atmosphere. And that's like putting more pieces of glass on a greenhouse. It's been keeping more and more of the heat in the atmosphere, and it's been heating up the planet. So that's basically what when we talk about the greenhouse effect. We have sun rays coming in, but they're not escaping as quickly as they did before. They're trapped by these greenhouse gases. And that's where a lot of our problems have been coming. And this is a complicated diagram, but it's actually quite simple. It's basically saying, where are those greenhouse gases coming from? And I'm not going to go into any great detail here, but there's carbon dioxide in the atmosphere. It goes in it cycles. It goes through the system. The problem is that it was all in balance, more or less in balance for hundreds and hundreds of years. But then we learned how to take coal and oil and burn it, stuff that was stored for millions and millions of years in the earth, full of greenhouse gases. And when we burn them, we release those greenhouse gases. So over the last 100, 150 years, we've gotten very good at finding old carbon and releasing it into the atmosphere. And that's the problem. We've been adding more and more greenhouse gases to the atmosphere, and that's the problem we're now having. So that's the greenhouse effect. The other thing, before I get into some of my slides, I also want to talk about two things we have to make sure we know what we're talking about. Climate versus weather. Weather is what you get today. So it might be minus 15, minus 17 degrees outside my building today. Say, what happened to the greenhouse effect? That's weather. That's what you get that day. Climate is the long-term trend. And when it comes to these issues, it's climate which you have to look at. Yes, you're always going to get some very cold days. Yes, you're going to get some very stormy days. And you might say, what happened to the so-called greenhouse effect? Well, the point is, it's not weather. We're not talking about day-to-day events. We're talking about the average weather. And that's what the whole ecosystem is changing. So we're talking about climate, not weather events here. We're talking about long-term averages, and that's important. So I said greenhouse gases are increasing. How do we know? Well, we know pretty well they're increasing for many ways, but I'll just talk about some of the ways that I work with my colleagues. And one of the reasons we know they're increasing is, first of all, some places have been measuring them. This is in Hawaii, the Mauna Loa Observatory, and it's actually been measuring greenhouse gases on the planet going back a long time. This is the measurements that went back to the 1960s, actually late 1950s. And this graph shows going up to the year, I think it's 2018, 2017, almost to the present. And you can see that they've been measuring greenhouse gases in this remote place in Hawaii. And you can see what's happened just since about 1958 to 2017, how much these greenhouse gases have increased due to human activities. Now, if you look carefully, you see they're going up and down, up and down, up and down. That's the Earth breathing. You can see that CO2 goes up, and then during the summer, CO2 goes down, and in winter, what it is, remember, plants take up carbon dioxide when they photosynthesize. So in spring, they start photosynthesizing very quickly. They suck up some of the carbon dioxide, less so in winter. You can actually see the Earth breathing in these high detailed measurements. So we know from at least this that since 1958, greenhouse gases have increased. How do we know they've increased over thousands of years? I should just say this is Charles David Keeling. He died recently, died about 10 years ago now. Here he is getting the Congressional Medal. He was honored for this work of actually showing that. How do we know that? Okay, so that's 1958, but what about, how do we know what it was like 100 years ago before the Industrial, so how do we know what it was like 1,000 years ago before the Industrial Revolution? Well, there's other ways scientists have learned how to find little different ways to get this. And one of the ways they do is the ice cores. And this is this type of work I do. We go back in time. I work on lake mud. Lakes slowly fill with mud, and it's like a history book. The older you go in the mud, the deeper you go in the mud, the older it is. And so I can go back 1,000 years and see what lived in the lake by the fossils that are in the mud. Ice core people do sort of the same thing. If you go to the middle of Greenland, there's over 3 kilometers of ice going back thousands of years. Every year, snow falls on the top of Greenland, and then a little while later, snow goes again on top of Greenland. And so you make like a history book of snow, and you go. It's actually over 3 kilometers of ice at the middle of Greenland. Antarctica is the same thing. They go back in Antarctica back 850,000 years, drilling into the Antarctic ice. And that's a history book of past climate in that part of the world. And the way they do that is with ice cores. These are quite extensive operations, but they drill kilometer after kilometer into the ice. And it's a history book. The deeper you go, the older it is. And in that ice, here they're looking at one of these ice cores, and just a part of it. As I said, it's kilometers long. They do about 5 to 10 meters at a time, 5 to 10 meters going back. Every time they go deeper, farther back in time. They can see many, many things in the ice cores, but one of the things they can do, this is some of the ice core under a polarizing microscope. And I think you can see those little dimples or like little pimples in some of the snow, some of the ice crystals. Those are gas bubbles. When the snow fell, it entombed some of the gas. And now it's part of that history book at the bottom of the lake. They can go back thousands of years and measure how much carbon dioxide, how much greenhouse gases is in those bubbles. I don't know how old this bubble is, but that bubble could be 100,000 years old. There's ways they can date that. And then when they do that, then they can decide how the greenhouse gases have changed, not just since 1958, but going back 1,000 years, 2,000 years, 850,000 years. So here's a figure. This is CO2 concentrations going back 850,000 years. This is the part that they measured in Hawaii, the red part. And this is the part that they ended up, you can see for 850,000 years from the gas bubbles, it's been remarkably steady, very little change in greenhouse gases. Then once humans learned how to use fossil fuels, they learned how to remove coal, how to burn coal. You can see this remarkable increase in greenhouse gases. So we do know that humans are causing this rise in greenhouse gases. And we can link it to things like automobiles and industrial activity and so forth. And so then the net result is the Earth is getting warmer. Most parts of the Earth are getting warmer. And you've probably seen some of these maps, but this is showing how much the Earth is going to warm. This is just how much the Earth is warm from 1958 to 2008. And you can see that large parts of the Earth are warming and warming very quickly. And you can see especially how fast they're warming in the Arctic and the Antarctic regions. And that's really, that's a significant part of Canada. About half of Canada is in the Arctic. So this is something we have to worry about. So why is the Arctic warming so quickly? Well, the reason the Arctic's warming so quickly, we often refer to the Arctic as the miners' canaries of the planet. The Arctic's the first to show signs of climate change, and they do so to the greatest degree. And just like the coal miners used to bring canaries into the coal mine, they have cages of canaries. And when the gases in the coal mine they were like early smoke detectors. When the gases in this coal mine got high, the canaries would get very agitated. And that was when the miners knew they had to get out of the mine. There's probably an explosion coming or something. We often refer to these as being the miners' canaries of the planet. The Arctic change is the first and the most. And why is that? Well, that's got to do because of ice and snow. And I use the analogy, the comparison, if you went out on a hot August day in a parking lot behind this building here, and you saw a white car and a black car or a dark car, you put your hands on both cars. They'd both be hot, but the black car would be hotter. And that's because the black car is getting the sun's rays and it's absorbing them. Whereas the white car is acting much more like a mirror. The sun's rays are hitting it and they're being reflected back into the atmosphere. That's one reason why in summer you wouldn't wear a sweater like I'm wearing here, a dark sweater. You'd wear probably white clothes or light clothes. If you're really hot, you want it to reflect heat, not to absorb heat. Well, the Arctic and the Antarctic in its normal state is like the white car, ice and snow. It's like one big mirror. It's reflecting heat. But you start putting in greenhouse gases. You start warming the planet. You start melting some of that ice and snow. And as you get less and less ice and snow, it looks more like the black car. It's more like the black car. It heats up more. It heats up more. It melts more ice and snow. And this is what we call a positive feedback. The warmer it gets, the more ice and snow melts. The warmer it gets, the more ice and snow melts. And that's why things happen so quickly in the Arctic. It's a bit like the white car, black car analogy. The same analogy, the same comparison might be, you go to a beach on a hot August day and you see a white chair and a black chair. You'll sit on the white chair. The white chair is not going to be so hot. It's not going to burn your back when you sit down on it. So basically, this is just what I said using a graph. This is an example of a positive feedback. As the temperature gets colder, you get more snow and ice. If you get more snow and ice, you increase the albedo. You increase the mirror, the reflectivity. So you reflect more of the sun's rays, and it decreases the temperature, so you get more snow and ice. You see, I don't want to say it's a snowball effect, but it's like a snowball effect. On the right here is what is the problem. You increase the temperature with adding greenhouse gases. You decrease the snow and ice cover. You decrease the reflectivity, the whiteness of it, and that increases the temperature, so you decrease more, and everything starts happening very, very quickly. A negative feedback is like a thermostat. This is exactly opposite to what you have a thermostat in your house. Thermostat in your house, you set a temperature. It's a negative feedback. It's always bringing it back to normal. It's not speeding things up. If it gets too hot, the air conditioner goes on and brings it back to 72 degrees. If it gets too cold, the furnace turns on and gets it back to 72. So that's an example of a negative feedback. It's exactly opposite what's happening in the Arctic. It's a positive feedback. So we have some issues here. Here we have sea ice is melting. You can see that this is a picture from 1979. You can see this. Just look at the Arctic island. This is where I work, in these Arctic islands up in the left. Look, it's completely ice covered in 1979. Look at it now. This is why you have cruise ships and some other ships going right through the Arctic now in summer. The sea ice is gone. It's been a remarkable decrease in the amount of sea ice, also changing reflectivity. And basically, again, I'm just showing you what I just showed you in the previous slide. it's all everything's speeding up because of this. You increase the temperature, you get less sea ice, the darker sea surface, it absorbs more heat, you get increasing temperature, everything's happening very quickly. And so here is an animation going, I hope you see it. It just shows you how much the sea ice has changed from the 1970s. Still quite a lot of ice. By the time you get to, now we're getting into the 2000s, you can really see, especially in parts like here where Canada is, less and less and less ice. So we really have now, good data, good data of what's actually happening. You put that on a graph. There it is. You can see that and if you said, oh, what happened in 1996? Everything's fine. It's gone back up. Oh, in 2001, everything's fine. It's reversed. You can't look at 1 or 2 years. If you look since 1980 to the present, there's no question what's happening. Yes, it's gone up a few times, but it didn't reverse. It just went back and back, so we have a real problem. So who cares about sea ice? Well, a lot of people, I'll use sea ice as an example now. A lot of people care about sea ice. One thing is polar bears. Polar bears get 98% of their food from seals. The only way a polar bear can kill a seal is pretty well from the sea ice. The seals come up with breathing holes. They're mammals, so they have to breathe there. They come up breathing holes. The polar bear waits for them, lunges them, but needs a solid platform to do that. So that's one of the reasons that polar bears are in trouble. They're having much trouble getting their food because the only way they can get their food is if there's a solid platform of sea ice. And this is what's happening. This polar bear cannot kill any seals standing on a piece of ice like that. Now, I've worked in the Arctic, and we've had some problems now with polar bears. Before, the polar bears in the summer, they'd be out there hunting seals. Now they're getting hungry. They can't get their seals. This is one of the huts we have. You can see a polar bear has torn through this hut. This is one of the huts we sleep in. You can see it was getting pretty angry. Knew there was probably food in there. It tore through the hut. And here it is. This is another bear that tore through our kitchen tent. Back, as you can see, we're up in the high Arctic. And here's one bear we saw. He came right to our camp. And it's a sad-looking bear, actually. It was trying to get food. And this bear is not healthy. This bear should be, this is the time when it should be eating on seals. And it's just not eating a lot of food, so it's not in good shape. Now, there's other things that are happening. Here you see an Arctic hare. You barely see it. It's excellent to show what its camouflage is. Arctic hares are adapted. They're like big rabbits in the Arctic. They're adapted to be in the snow and ice because they have this white coat. And foxes try and eat them, and other animals try and eat them, but they're almost invisible. If they are this Arctic hare with this white background behind them. What's been happening when the snow's gone, they're not so invisible anymore. And of course, they've never seen humans, so they're not scared of humans. You could come right up to him. But this guy thinks he's invisible. He thinks he's usually his best defense sometimes just to stay put because very few people can see, very few predators can see him because he's white. But the snow's gone. So if the snow's gone, you're going to have some trouble dealing with that. Now, there's people say, well, who cares, about polar bears? Who cares about hare? Well, the thing is that people do live in the Arctic. Canadians live in the Arctic. Many of the Inuit live right on these small coastal communities in the high Arctic. And many of them still have a somewhat traditional lifestyle, and they hunt off the ice. If the ice is no longer there, they can no longer hunt. And they also use the ice. It's like their roads, their roads are disappearing. Also, never mind the ocean ice. Especially in the subarctic or the Western Arctic, people use the rivers that freeze as highways. There are no roads up there, so the only way to get up there is they send trucks with all their supplies going up these so-called ice roads. Well, those ice roads are melting. They're no longer secure to move goods, move food and stuff. There's some massively long ice roads here. Here's one that's 550 kilometers long. And what's happening is people are going right through the ice roads now, and that's a major issue. People can't get their food, they can't get their supplies, because that was one of the few ways, as opposed to flying it in, it's extremely expensive. one of the few ways to get supplies in was through the ice roads. And this actually is affecting many northern communities. As it says here in the headline in the CBC story, winter roads have essentially become a way of life for the communities, and these winter roads are decreasing. So the only way that you can, if you can't hunt for your food, and your food's not coming in on the ice roads, the only way is then to go like to the northern store, like the Hudson's Bay Company, which might fly in the food. But this is not the traditional way to buy your food. And if you look at the prices of the food, it's really quite remarkable. I mean, many of you in the audience don't have to buy food yet, but look at this. Here, seedless grapes, about $20 a pound. Here, look at the onions, $10. Here's how you, one whole chicken, about $13. This is not the traditional place to buy food. Not only is the sea ice and the river and lake ice disappearing, but also we're getting what we call land-based ice. So sea ice is floating on the ocean. Lake ice is floating on lakes. One of the biggest problems is ice and snow that's on land is melting, and that's going into the oceans. So that would be like on the, Greenland's one enormous island. That ice and snow on Greenland is melting. It's going into the ocean. One thing that's happening is the ocean, because now we're getting more water, sea levels are rising, getting higher and higher. They're rising for two reasons. One is melting from land-based ice, from things like Greenland or the land. Another is just warm water actually expands, as you may know, so it's also causing some of the increase. The problem is the oceans are increased. If the oceans increase in water levels, that means there's less land. You're going to start flooding land. And that's exactly what's happening. And that becomes a major issue with hurricanes, extreme weather events. The higher the ocean, the farther inland the ocean water gets. So that's why you get some of these massive hurricanes now that are causing all sorts of problems. Another problem that's happening is much of the Arctic has what's called permafrost. Permafrost is soil, rock, or sediment that is frozen for more than 2 consecutive years. So the Earth is frozen. But what's happening, and it has this active layer that always would thaw, this talic, what they call talic, would never would thaw, but it was this permafrost. The talic would thaw, sorry. It's a permafrost that was permanently frozen. What's happening is the active layer is getting deeper and the permafrost is starting to thaw. And when that happens, here you see permafrost thawing, the whole land above it starts falling apart, falling down. So that looks nice. When you see a picture like that, it looks impressive, but it's less impressive if your house is on it. If your house is on it, your house, you assume the house is on steady ground. But if the ground is starting to thaw, the whole house starts falling. Entire communities are disappearing because the land is crumbling below them. Also roads, these are roads that are buckling. These roads are not very good to go on anymore. The permafrost is thawing underneath, as you see, and the whole road is starting to buckle. So this is costing a lot of money for infrastructure. That's just a few things in the Arctic that are happening with climate change. We go to the Arctic because that's where we get a lot of ideas of how things change. But I call the climate change the new threat multiplier. And by that I mean, virtually every time the Earth gets warmer, other problems happen. That's in the Arctic, but it's also happening here. You'll notice I work on lakes. Many of the lakes have less lake ice. The ice thaws earlier. The summer has gotten longer. Many of you may have cottages, and you've noticed that algal blooms, blue-green algal blooms are increasing. We have linked those to a warmer, longer summer, for example. Many of you may have noticed there's fewer trout in the lake you might have gone fishing in. Again, with a longer, warmer summer, there's less oxygen in the deep water for the trout. These are some of the things we work on in my lab here. So it's not just warming, it's affecting all these other things that are happening. So in summary, that's my talk. I don't want to sound too depressing, but it's a very serious issue. And I think it's important that we deal with the issue and start dealing with it very, very quickly. So I think that's my presentation, Ben, if that sounds good.
Well, thank you, Dr. Smol. Just before we move into the Q&A, I'd like to remind those classrooms joining us live to direct their questions to the Q&A, which is located in the bottom center of your screen. So our first question today comes from Ms. McKee's classroom, and they have been learning about the importance of water, and they'd love to know more about how climate change is having an impact on our waterways, both locally and globally.
Yeah, so I work on water, and it's a very important issue that we deal with. And it depends where you live. And it's really going to, very different things are happening in different parts of the world. So within Canada, one of the issues is, we get two things happening sometimes, but in many parts of Canada, if there's more heat in the summer, you get more evaporation. And if you get more evaporation, water levels go down. So that's something people see. It looks like their shorelines are getting longer. while the oceans are increasing in volume, many lakes are decreasing and they're evaporating away. And so right away, you start seeing more exposed shoreline. You start seeing all the contaminants that are in the water have now been concentrated to some extent because there's less water to dilute it. And you also start seeing changes in the biology of the lake. Because the summer is longer, you tend to make the conditions much better for algal blooms, that those green scums that you get in summer. They can actually cause some pretty serious problems. So that's what we'd often see in, say, Ontario lakes. Now, if you go out west, where say parts of Alberta, Manitoba, and Saskatchewan, we have these these shallow lakes that are salty. If it evaporates, the lakes get saltier and saltier and saltier, so much so that they can actually start killing the organisms living in there. So just think about it. It's like putting I use the analogy, the comparison. If you put a pot of soup on the stove and you take the lid off and you put the heat on low and you watch it, two things will happen to your soup. One, the soup level will go down, 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 down. That's because the water's evaporating away. That's what's happening in the lakes as they evaporate. The second thing, if you keep tasting your soup, it's getting saltier and saltier and saltier. That's because water is evaporating, but it's leaving the salts behind. So that's another example of how you're completely changing not just the volume of your lake, but you're completely changing the chemistry of the lake and making it far less available. Now, then there's other things. If you go to places that depend on, for example, mountain snow or mountain ice as your water supply. And a lot of people do depend on what we call ice caps from mountains. We also work in Ecuador and Peru. A very large part of the agriculture is based on water that melts from the ice caps on the top of the Andes Mountains, and they go down and they use that for agriculture. Well, right now it's getting so warm, it's melting very quickly. They're like water towers that are emptying very quickly. Soon there won't be enough water, and then you're going to have all sorts of issues with agriculture. So the list goes on and on. It affects all aspects of water, and so it really is becoming a major issue.
Well, thank you. Our next question today comes from Ms. Brzezinski's classroom. I hope I'm pronouncing your name correctly. And they're wondering, what can we do to make this better? What things make the biggest impact?
Yeah, this is always the big question. What can we do? And a lot of people say, oh, I'm one person, I can't do, I'm one, and it keeps going. I'm one village, I can't do anything. I'm one city, I can't do anything. I'm one province, I can't do anything. I'm one country, I can't do anything. The trick is, like with every problem in history, every environmental problem in history, it's individuals that have to start and get things moving. And we have to very seriously cut down our greenhouse gases. And that's not simple anymore. You know, I was arguing for this for 25 years. It was simpler 25 years ago, but we've waited so long. The easy solutions it's too late for the easy solutions. And there is no one solution. People are always looking for the silver bullet. It's too late for that. It's a silver buffet. We have to do about 10 things at once. But it's mainly, we got to get off fossil fuels. So there's different ways we can do that. I mean, and some of them are simple ways. We don't have to drive everywhere. We don't have to drive a personal car that weighs a ton to go and get a liter of milk or something. You know, we start walking more, taking public transportation more, start thinking about electrical vehicle. We're all going to be thinking about electrical vehicles very soon. Every time you use greenhouse gases, every time you do something, you're increasing greenhouse gases. You have to learn how to try and avoid doing that. Another issue is heating your house or cooling your house. Maybe put on a sweater. Maybe the house doesn't have to be so warm in winter. Maybe it doesn't have to be so cool in summer. That's another issue. So we have to stop on our own individual level. We have to show our own leadership in cutting down every time we think of using greenhouse gases. And that's one way. Second way is, so that's our individual actions, let's say. Second way, we have power of our wallets, how we spend our money. Now, I mean, many of us are still students, but very soon you'll be spenders. You'll be deciding where the money goes. And we can start making decisions of how we spend our money, where we invest our money, the types of products we buy, and start realizing that maybe I'll pay a little bit more on something that isn't going to be causing greenhouse gases than something that is, because it's a real issue of a problem. And eventually, the students in these classrooms are going to be citizens who vote. The third thing is the vote. We live in a democracy, and we have the power of politicians will listen to people if enough people say it's an important issue. And that's really what it comes down to. I think the main thing we have to do is appreciate I argue this is the most important problem that has ever faced humanity. You watch the news at night and people talking about immigration. They're talking about the economy. And, all these things are issues that obviously politicians have to discuss. But why is not every night the lead story on climate change? It is without a doubt the most important story, I would say, in the history of humanity. And we don't seem to have appreciated it. So I think an overall theme is to start appreciating we have a problem and how to deal with it. And that's the first step in solving a problem. We can solve it, but that's the first step in solving the problem.
So I'm seeing this question come from a couple of classrooms, and they're wondering, given how dire things look, is climate change feasibly something we can do about? And if so, what does our timeline look like for that?
Yeah, I get that question a lot. The fact I still rage means I still have hope. But it is very late in the game. We should have, I don't want to keep saying this, but we should have dealt with this. We should start listening to scientists. By and large, scientists in universities and elsewhere are paid by tax dollars to a large extent, not totally. Why do we pay scientists to find out things that no one wants to, I don't want to listen, type of thing. But so it is not too late, but it's very late. Let me put it that way. It's already too late to, we're going to see effects. Every time we add more greenhouse gases to the atmosphere, we'll see bigger effects. Let me put it that way. We can still deal with, if we can keep climate change below 1.5 degrees, which is what people are trying to do with the Paris agreements, we can survive that reasonably well. We'll still have some hardship. If it goes to 2 degrees, it's a lot more hardship. It goes 2.5, 3, then it's just up and up and up. So it's a question of pay now or pay later kind of thing, That's one of the problems with climate change, is in the future. You see people with my hair that's gray, I'm going to turn out okay, I'm going to survive this one, But people like you or the students in the class, I don't want to sound depressive, but they're going to have to deal with this, it doesn't help pretending it's not a problem. So I think we just move on along those lines. And so it's not too late, but it's already too late to have no effect, but it can go much worse than it is now.
So how do things like pipelines, carbon taxes, and recycling programs intersect with climate change?
Well, they all intersect to some extent. Let's just talk about so-called carbon tax. First of all, it's amazing how some politicians, scientists, were so bad at public relations. I would never call it a tax. You put tax on something, everyone thinks it's something bad. But how about carbon pricing? If it's free to pollute, my view is people will pollute. So if you put a price or a penalty on it, people will not pollute. And that's been shown, and that's not rocket science, that's just a fact. So if it's more expensive, if it's cheaper to buy a product that will pollute, people will tend to buy the cheaper product without thinking. The problem is the products are not priced properly. Nowhere in the price of some of the products we buy are the environmental costs, which have economic costs that we all have to face. It's almost like the pricing system is wrong, So putting something like a carbon tax is trying to fix that to some extent, saying if you're going to go and use, say, a car that takes out 5 times more emissions than this car, you should be paying a penalty for taking that car that might be cheaper, but it's hurting everyone. Everyone else is paying the price of you buying a cheaper car or cheaper product that's going to pollute more. So it's a way of equaling that. And I like some of those strategies that when they have this pricing, this carbon pricing, that it goes back to the people. It's not actually a money grab for politicians. It would go back into healthcare or going back into something else, that's coming up. So they all intersect. The products we buy all intersect. You can buy low carbon products, high carbon products, what you eat, the types of things you eat, how you get from A to B, all that is part of it. And that's why it's such a complex problem. There's so many things that are happening. Even pipelines. I mean, if you're going to use oil, what is the, I realize we're not just going to tomorrow stop using fossil fuel. So let's make them the most efficient way of using the cleanest fossil fuels we can and move them in the most efficient way. So all those things intersect. So it's very complicated, but the net result has to be fewer greenhouse gases going into the atmosphere.
The grade 4s at St. Francis in Mr. Turner's classroom are wondering how many greenhouse gases are released by snowmelt?
By snowmelt?
By snowmelt, yes.
The greenhouse gas isn't released by the snowmelt itself. So melting snow itself isn't doing it, but if it what it does if it exposes dark ground, that heats up the planet. And that also, there is an indirect way. If the snow disappears, like let's say, I'll use a large part of the Canadian North is like a peatland, let's say. If that peatland is frozen and cold, peatland is old mosses, old plants. It's full of greenhouse gases, really, that have been preserved in the peatland. If you remove the snow itself is not releasing the greenhouse gases, but now the peatland might start melting, decomposing, and that will be releasing greenhouse gases. So it's like a one-step removed from the snow.
So we've had a lot of great questions asked today. Unfortunately, we're running out of time, so I won't be able to get to them all. But just before we finish up today, I was hoping to have you talk a little bit about your career path, how you ended up here, and maybe some advice you have for students who are considering something similar for their future.
Yeah, well, I mean, I grew up in Montreal, urban Montreal, and I grew up mainly in the 70s, let's say, and that 1970s. And that was a time when the environmental movement was gaining some steam, and I got interested in the environment. It was also the time when, now they're quite common, but they were starting to get like documentaries. There was Jacques Cousteau, who was talking about the oceans. And I was at McGill University, which is a major university in Montreal, and they had a marine biology program. And I thought, I kind of looked, people go out on a ship, they looks like they go fishing and they get paid for it. Sound like a good deal. So I got interested in marine biology. While I was in that program, I found out about you can actually have a career working on lakes, which sounded even better. Sound like people can go canoeing and fishing and get paid for it. It's not quite that simple. I worked pretty hard, but it looked pretty good. And so I did my degree in biology, and then I kept going in this field, doing my master's and my PhD. So I was very interested in lakes and the environment, and it's a very privileged job to have. I like to teach, I like to find out things and what happens. So much of what I do is learning about the environment around me. So my advice is to anyone who's interested, education's very important. You learn how the world runs. And I would say do what you love. And if you do what you love, you probably will be pretty good at it. And I have the best job in the world because I don't really think I have a job. I look forward to coming to work every day because it's going to be interesting. I'm going to be talking to interesting people, and I'm going to be finding out things, and I get to travel and do research in the Arctic and very nice places like this. And I feel like I'm doing something important. So do something you love, something important, and you'll probably be decent at it.
Well, that's all the time we have today, but thank you so much for taking the time to talk with us about this important topic and for taking all of our questions.
Thank you. Well, thanks for having me.
So next time we are back with PIR Live Event on March 26th with Dr. Pete Hollings from Lakehead University. More information about these webinars and other PIR educational programs are available at pirweb.org. Thanks for tuning in and have a wonderful day.